Welcome to the future of factory automation.
This program is a broadcast of a Japanese podcast that has been translated into English using Notebook LM.
And in this deep dive, we're going to be exploring the really fascinating world of factory automation. We'll be looking at a translated discussion between industry professionals.
Right. And our mission here isn't just to, retell their stories, but to pull out some key insights. Insights into the kind of ingenuity the field demands and also the complexities of the software that makes it all run.
Exactly. The original conversation kicked off with a pretty straightforward question, actually.
Mhm.
It was about memorable software experiences, both the good and the bad.
Yeah, and interestingly, before they even got deep into the software side, one of the speakers shared this great story. It really sets the stage for the kind of resourcefulness you often see in factory automation.
Okay, let's unpack that one first, because it sounds like a perfect example of, making do with what you've got. The core problem was a machine with a vibrating belt, right? Causing issues with stopping the workpiece accurately.
That was it. And normally you'd think, okay, let's put some vibration sensors on it.
The standard approach, yeah. The buy-the-book solution.
But budget constraints.
Ah, the classic problem. They mentioned the sensors were pretty pricey, like 200,000 to 300,000 yen.
Yep, significant cost. And the key thing was they just couldn't get the purchase signed off. No approval.
So faced with that, what do? They couldn't just ignore the vibration.
They got creative. This is where it gets good. It really shows that expertise in automation isn't always about having the fanciest tech. Sometimes it's about truly understanding the problem and using whatever tools are actually available.
So what was the tool?
They borrowed a high-speed camera.
A camera. To fix vibration. Okay, interesting angle.
Instead of measuring directly, they decided to film the vibration. But the really clever part was how they measured it.
Go on.
They literally just placed a ruler in the shot right next to the vibrating belt.
Seriously?
Yeah.
A ruler. That's brilliantly low tech.
Isn't it? It really speaks volumes about just figuring things out on the fly.
So they film it, ruler and frame. Then what?
Then they played the footage back, nice and slow motion, and they manually measured the amplitude, how much it was moving frame by frame, using the ruler as a reference.
Wow. That must have taken some serious patience, just stepping through it.
You can just picture it, can't you, that dedication? Did they mention how long it took?
They didn't get into the specifics of the time involved, but the reaction of one of the speakers summed it all up perfectly. He just said, "This is FA." Yeah, factory automation.
Huh. Yeah, that says it all. That single phrase just captures the reality, doesn't it? Finding solutions, often under pressure, often with limits. Adaptability is everything.
Okay, so that's a fantastic story of ingenuity. But it also brings us to the flip side. The original question was about good and bad experiences.
Yeah.
So what about the less pleasant software encounters?
Right. The conversation then shifted towards the, let's call them terrible software experiences. And a big theme that came up was dealing with software libraries from manufacturers.
The joys of third-party code.
Exactly. The major frustration seemed to be getting these libraries with really poor documentation, or sometimes just no documentation at all.
So you've got this black box. It's supposed to do something useful, maybe control a specific device or perform a calculation.
But you have zero insight into how it's actually doing it internally.
Nightmare scenario for troubleshooting.
Absolutely. And they specifically called out receiving libraries written only in instruction list or IL code, that mnemonic stuff.
Okay, for listeners who aren't deep into PLC programming, maybe explain IL a bit. Why is getting only IL such a pain point?
Well, think of IL as being very, very close to the metal. It's like the PLC's native tongue, almost machine code. It's fast, it's compact, which was great for older PLCs with limited memory and processing power. You see it a lot from overseas manufacturers, historically, Siemens, for example.
Okay, efficient, but...
But it's incredibly difficult for humans to read and understand, especially compared to, say, ladder logic or structured text, which are more abstracted, more human-readable.
So the library works, the machine runs, but if something goes wrong, or you need to modify how it interacts with something else.
Good luck figuring out what's happening inside that IL code without the original source, like the ST code it might have been written in. It's like trying to edit a complex document when all you have is a printout, not the original file.
That's a great analogy. You're stuck trying to reverse engineer it.
Yeah.
And that ties into another issue. They mentioned structured text code just disappearing. How does that happen?
Yeah, that's another common headache. So you might program your system using nice, readable, structured text, but when you later connect to the PLC and upload the program from the CPU...
You don't get your ST code back.
Often, no. especially if the original project file containing the ST source wasn't saved separately or isn't available. The PLC only needed the compiled version, the IL, to run, so that's all it stores internally.
So the readable version is lost, unless someone was diligent about saving the source project file elsewhere.
Precisely. You're back to staring at low-level IL, trying to figure out the logic that you know was once written much more clearly.
Man, sounds frustrating. It makes you wonder about the history here. Why start with IL if it's so hard to read?
Well, the very first PLCs were programmed directly in IL. It was the most direct way to give instructions to the processor. Ladder logic came along later.
As a more visual way.
Exactly. It was designed to mimic the relay logic diagrams that electricians were already familiar with, made the transition easier for them.
So the ladder diagrams were sort of a graphical front end.
That got translated or compiled into the IL that the PLC actually executed behind the scenes.
Interesting. And they even mentioned that some old-school relay-based systems are still out there.
Apparently so, though it's rare now. The thinking was maybe they just haven't been updated. If it ain't broke, don't fix it, perhaps, or cost.
Makes sense.
Okay.
Okay, shifting gears slightly, back to software libraries. They talked about function blocks, mentioning Siemens specifically. What was the issue there?
Function blocks are powerful, right? They let you package up complex logic into reusable blocks. But the point made was that some manufacturers, and Siemens was the example given, can have really deeply nested parameters within these blocks.
Great.
Meaning you might have a block, and to configure it, you go into its parameters, and then those parameters have subparameters, and maybe even more levels deep. It makes the blocks very versatile, potentially, but also kind of opaque.
Hard to see the whole picture of what's going on inside.
Exactly. You lose transparency. It's powerful abstraction, which is good for simplifying the main program view. But when you need to debug or really understand the nuances of how that block works, digging through all those nested layers can be tough.
Another black box, almost. Just a more structured one.
Sort of, yeah. It highlights that trade-off between powerful pre-built components and the need for clarity and debuggability. Good documentation becomes even more critical then.
Which brings us neatly to the next point, something universally understood in programming, I think. The nightmare of code with no comments.
Oh, yes. This isn't strictly a PLC software issue in terms of execution, but it's a massive human issue. Trying to understand uncommented code, especially complex automation logic written by someone else years ago, it's painful.
And even worse if you're trying to integrate systems, right? Like moving from one PLC brand to another. They mentioned Siemens to Beckhoff.
Yeah, imagine trying to port logic or just understand an existing Siemens program to interface it with a new Beckhoff system, and there are zero comments explaining why things were done a certain way.
They talked about literally having to compare I/O lists and memory dumps side by side to try and reverse engineer the flow.
Painstaking work. Hours and hours spent just trying to decipher the original intent. It's like archaeology sometimes.
But this is where structured text offers a real advantage, they pointed out.
Yes. A key benefit of ST, especially following the IEC standards, is that you can directly attach comments to the variables themselves.
Ah, so the explanation travels with the data point.
Exactly. And modern programming environments, IDEs like Code Assist, they often show that comment automatically when you just hover your mouse over the variable name in the code.
That's hugely helpful for readability and maintenance.
Massively. Now, some people argue, oh, if you use really clear variable names, you don't need as many comments.
But the speakers in the discussion disagreed.
Strongly. They made the point that good names tell you what a variable is, like motor speed, but comments tell you why. Why is the motor speed set to this value here? What's the context? What condition does it relate to? That's the stuff comments convey.
That makes total sense. The intent behind the code. And speaking of variable names, even choosing good ones isn't always straightforward, is it? They had some stories there, too.
Oh, definitely. They shared some pretty funny or maybe alarming examples of terrible variable naming they'd encountered.
Like what?
Like using food names. Variables named tomato or apple potato.
You're kidding? Apple potato. What could that possibly represent in a factory machine?
Who knows? That's the point. It's completely meaningless. It just shows a total lack of convention, or maybe someone thought they were being clever. Either way, it makes understanding the code impossible without asking the original programmer, assuming they even remember.
It really highlights that good variable naming is a skill. It needs thought and rules.
Absolutely. And then there's the related problem of using localized slang or nicknames for things.
Ah, the inside jokes that become technical terms.
Pretty much. Imagine trying to troubleshoot a machine where a specific movement is always called the backdrop by the local team, and even the button is labeled that way.
If you're new or from a different site, or worse, a translator, you'd have no clue what backdrop means functionally,
None at all. They gave another great example, calling a specific area of the machine Onigashima,
which means
Demon Island in Japanese. Apparently, it vaguely looked like one. A Polish translator working on the manuals was, understandably, completely baffled.
I bet. And the choo-choo train one?
Yeah, Kisha Papo. Apparently looked like an old steam train, so that became its unofficial but widely used name internally.
Hilarious, but terrible for clear communication, especially across different teams or languages.
Exactly. It just creates unnecessary confusion and relies on tribal knowledge that isn't documented anywhere formally.
So the solution is standardization again. What did they recommend for variable naming best practices?
Stick to the standards, PL-COPE coding guidelines, IEC standards. Use prefixes for data types like X for Booleans, true-false values.
Makes sense. You see X limits switch input, you know it's a Boolean signal.
Right. And use camel case for readability, like motor speed command instead of motor speed command or motor speed command. Consistency is key.
And applying these rules consistently across projects, across programmers.
That's the ideal. It makes everyone's life easier in the long run. Less guessing, more understanding.
Okay, this focus on variables leads nicely into another topic. Designing programs using variables versus using direct memory addresses. They seem to prefer the variable approach.
Overwhelmingly, yes. The big advantage of designing with variables is that you let the programming environment handle the actual memory allocation. You don't have to manually say, okay, inputs are in memory range 100 to 150, outputs are 200 to 250, internal flags start at 500.
Which sounds tedious and prone to errors like overlaps.
Exactly. With variable-based design, you just declare a variable like process temperature, give it a data type, and the system figures out where to put it in memory. It avoids clashes and makes adding things much easier. It's like using names instead of numbered cubbyholes.
Much more flexible. But they did mention it's not perfect. Still some challenges.
Yeah, it's not a silver bullet for everything. Things like indirect addressing, where you want to access a variable based on the value of another variable, or using pointers, or transferring large blocks of data efficiently, can sometimes still require you to work with structures or be more aware of the underlying memory layout.
Especially with communication protocols, like sending lots of data over Ethernet EP.
Right. You might need to define specific data structures to organize that data payload correctly, which can feel a bit closer to managing memory blocks, even if you're using variables within those structures.
So still some complexity there for advanced stuff, but for general logic, variables are the way to go. What about the old way, address-based allocation? What are the main drawbacks they highlighted?
The biggest one is rigidity. You define your memory map at the start. This range for inputs, this for outputs, this for timers. If you suddenly need way more timers than you allocated space for.
You're stuck. Or you have to painstakingly remap everything.
Exactly. It's inflexible. You hit the ceiling of your allocated range, and you've got a problem.
Yeah.
Variable-based design generally avoids that whole headache. The system just finds more memory space as needed.
It really sounds like moving toward variable-based design and following standards like IEC is the way forward, making code more portable, easier to understand between different PLC brands.
That's definitely the direction things are moving, and the hope. More standardized approaches mean less time fighting platform quirks and more time solving the actual automation problems. It lowers the barrier between different systems.
You know, it's interesting that they ended by circling back to that high-speed camera story.
It really stuck with them, didn't it? And you can see why it's such a perfect, tangible example of that resourcefulness we talked about. Ingenuity born from limitations.
It kind of grounds the whole discussion. Amidst all the talk of complex software, IL code, function blocks, naming conventions, there's still this fundamental need for practical, hands-on problem solving.
Absolutely. It's that blend of high-tech systems and sometimes surprisingly low-tech solutions.
So wrapping this up, our deep dive into this translated chat really highlights that duality in factory automation. You've got incredible ingenuity, like the camera trick, sitting right alongside the complexities and frustrations of legacy code, missing documentation, and just the general challenges of making sophisticated software work reliably in the real world.
It really drives home that you need to understand both sides, the physical process, the hardware, and the software, with all its quirks and history.
And it definitely makes you think about that balance in your own work, right? When do you reach for the high-tech sensor, and when do you need to, well, grab a ruler and a camera?
A great point. So maybe a final thought to leave everyone with.
Yeah, let's do that. Given this whole journey we've discussed, from direct, low-level instructions like IL, moving towards more abstract programming like ST and function blocks, but still needing these clever, practical workarounds, what fundamental skills do you think will be the most valuable for automation professionals trying to navigate the future of this field? What really matters moving forward?